Yes, I do need those back. I still haven't gotten the ENP copies.
Huh.
The purpose of the idea is that it's supposed to be sort of hopefully a reminder that as long as you put in your best effort, then it's all for God's glory. So I suppose that means that if you put in substantially less than your best effort, then maybe it's not a good thing. But anyway, okay. All right, I'm going to go get another pen because I don't like writing in red when I'm videotaping, and I don't see the black around the room, so I'll be right back.
Assuming that you're going to get one right. Looks like you crossed that.
Yeah, I got older.
I don't know.
I just put
No, I didn't have 0.8.
I had
0.4%. Nah, that can't be right.
Yeah, that's
Point 0.4%?
I put, that's what, that's why I have to have an extra zero on there. It's crazy.
All right, on the SDG thing too, it's a way that there are a number of composers who put that at the end of their composition. Handel, Bach, Johann Sebastian Bach.
So is that one of your compositions?
SDG, or so we go for it.
Back.
Sort of, no, I'm not saying I'm a famous composer, but maybe you guys are. Maybe your test is a masterpiece. I'm presupposing. Okay. Last time we talked about Fermi energies. Everybody remember Fermi energy? Or you want to, actually, let's see if anybody has questions about the test. I should not just cruise on. Does anybody have questions about the test that they haven't already asked? Nothing. You just sit in silence as you look through.
Why did you figure it out?
Hello, darkness, my old friend.
I'm going to talk with you again. All right, I don't have Garfunkel's voice to go high, so. Name of the song.
Sound of Silence. Simon and Garfunkel.
Nothing else? No other questions
On the test?
on the test?
Is it like, can you ask questions about grading?
About what?
Grading, or is that?
Sure, you can ask questions about grading.
So, +1 here, but it's a 0.
Because you have a minus one over here, so that one's not involved. That's to cancel each other out.
Right.
Okay?
1 minus 1.
Yeah. Okay. I know, arithmetic. Yeah, kind of stuff.
How many bonus points were possible? Oh,
3. 3 were possible. Oh, okay. So bonus points, you get 2 points for getting the 2 correct answers, which are injection molding and blow molding, and 1 additional point for not checking anything else.
So if you check all of them, we would have gotten 2 points.
If you check, no, because now we did subtract additional points for that.
Okay.
It's tricky with 3 points.
+1. Yeah.
Why?
Because we all need to think that there's 3. Because I got these 2, I was like, it's got to be one of these. Can't go in the middle to it, it has to be one more.
I didn't thought that, but that's okay. I actually just chose 3 points because I wanted 3 points.
I'm glad that that is the most tricky that you get on these tests. Like everything else is honest. It's not like a Gagner test.
Yeah, that's on video. Right?
I know.
All right. Any other questions?
Do you know what the average is?
Do I know what the average was? I don't recall.
Well, you can add up everybody's grades.
All right, we're put your papers in the middle. We'll find out.
Okay. What did you get?
I can quickly check, hopefully. Maybe quickly. I don't know. We'll see. Anybody else have questions? While I'm stalling to answer Cassie's question.
How was your day?
They told.
Really? All right.
I said in an hour, it was only 24 minutes.
That's a clear office reference. Full grade.
And then I said, then I showed the radius instead of the diameter.
Yeah.
So there's 2 points. What's the third? Hold on.
Seriously?
Oh yeah, no, I would have got a perfect score on that if I didn't say that. 24 minutes in an hour and the radius instead of the diameter. And that was the one where I was just like, I have no clue how to do this. I know, right? I know. It makes me so mad. I'm pretty
Graphite fibers?
I don't remember off the top of my head. Who got 7C correct? And can tell me what the weight percent graphite fibers is.
80.7.
There you go.
80.73.
Yeah, I agree with Britton.
What's that?
You just said 80.73 as opposed to 80.7.
Shut up.
Okay. I'm sorry, I can't find the average. My phone not loaded, so I'll have to go down.
No, I sent it to your.
Pretty sure it's in the 80s. Don't know where. First test was in the 90s, was like 90. Second one I think was like 85, 86. All right, any other questions? All right, then we're gonna call it done and we'll move on. All right, so last time we talked about Fermi energy. Remember Fermi energy? The energy, you have a 50% probability of finding an electron at any particular temperature. Okay. So, today we're going to talk about thermocouples and how they work. Well, at least that's what's next. We got more stuff after that too. All right. So, we have the Fermi energy here. And then we increase the temperature. The distribution looks like this. And then if we increase the temperature further, it looks like that. So this is T1 greater than 0, and this is T2 greater than T1. Everybody understand that, right? That's where we were with the Fermi energy. Okay, so what that means is if we heat one end of a wire hotter than the other end of the wire, there are going to be some electrons excited to a higher energy state at one end of the wire than they are at the other end of the wire. Does that make sense? So there's going to be a force then, because it's an energy gradient. You have high energy electrons down here at the hot end, and no high energy electrons down here. So it's going to be an energy gradient, which is going to cause a voltage, energy per charge, across the length of that wire. Does that make sense? See what I'm saying? You energize the electrons on this end, and they're going to want to move that direction. There's a voltage going to push them, because there's an energy gradient along the wire. So there's going to be a voltage that's proportional to the temperature change, because as I get higher temperatures, I'm going to get higher voltages, higher energies. Okay. So different metals, though, respond differently to different temperatures. So if I take another metal and heat it up to the same temperature range, that other metal, you know, relatively speaking, might do something like this. Right? Because it depends on how many electrons they have, where the energy levels are, that kind of thing. So what you end up with is if you take two metals then, the red metal and the blue metal, and connect them end to end, placing this end under a flame, on this end, you know, in a cold, you know, in a cold state. So cold on one end and hot on the other. They're both going to have some kind of voltage pushing electrons from the hot end to the cold end. But since VA is not equal to VB, let's say that VB is greater than VA. Nope. That's the way I drew it. VA is greater than VB. There's going to be a bigger push there. I'm going to get a net flow of electrons in the loop in that direction. That make sense? So that there's a net voltage. Now, if this is 0, then there's going to be some V total, which is equal to VA minus VB, which is greater than 0. And so, if I just, let's put some constant, let's say that V is some constant proportionality, that says then it's going to be equal to alpha A minus alpha B times delta T. And as long as delta T is in a fairly small range, this is indeed linear. And we have a linear relationship between the measured voltage and the temperature difference between the two ends. All driven by the fact that they have different Fermi energy, different Fermi functions, different energy distributions, based on the relative position of the Fermi energy compared to their conduction bands. Yes?
Would I be correct in presuming this is not how batteries work? And like,
Well, it depends on what you mean by a battery. But yes, it's not how batteries work. Batteries convert chemical energy into electrical energy. But there are ways of powering devices that use this phenomenon.
so we could like hook two ends on like the end of a circuit and have two different kinds of wire and heat it, and it will get some charge.
And then we'll get, exactly. So there are thermoelectric coolers that work on this principle. Right? Things we're looking at for the capstone project. The thermoelectric cooler works on this principle. So thermoelectric cooler, in the case of a thermoelectric cooler, it's active. So we're applying a voltage and causing a difference in temperature. But it's no different than all we're doing is just, you know, the input is a different end, you know, or a different side of the equation. Or we could just take the same thing, expose one end to a higher temperature, and we create a voltage. It's the same thing. Okay. Let's see. Oh yeah, one more thing. The thing that's particularly helpful here, if you go through the math, it turns out it only depends on the temperature at the junctions. The intermediate temperatures don't matter. So I can use my thermocouple in any surrounding environment. All it will measure is the temperature. You know, the voltage will depend only on the temperature at the point where the two pieces meet. Okay? And what's more, if on one end I have, where's my green? If on one end I have another wire, barely green, but anyway, if I have another wire connecting these two, as long as those two junctions are at the same temperature, it doesn't matter. The voltage will only depend on A and B. Yeah. So these two don't even have to be connected on this end. I can connect them to some kind of probing device. As long as the probing device is at a fixed temperature, I can measure the voltage and it's only dependent on the temperature, the relative temperature difference between that end and the probing device. Yes?
What if you had like, I don't know, it's like you had red and you had purple and you had blue and then green and then they connected, how would you calculate that ratio?
And red and purple.
So like, if you had like two different kinds of wires on like the VA and you had two different sides from the other for VB, would you just have to just calculate a new, figure out what the new VA and VB were?
And what happens if we did this on Mars? What would the effect be? Yeah,
Okay.
Yeah, I guess, I don't, yeah.
No.
There would be potential along all of them, right? If I had 4 wires connected, then there would be some kind of potential along each of them. They would be essentially creating parallel circuits, and you'd have to actually do a parallel circuit analysis to find out what the actual potential is. Why you would do that, I'm not sure, but it's up to you. Okay. So you've heard of Peltier cooling? Who's heard of Peltier cooling? One person.
I just heard of it.
Okay. This is Peltier cooling. That's what you're doing. So I can use it to measure temperature or to drive temperature, either way. All right, that's thermocouples, electric properties. Next, any questions about that before I move on? Just kind of going through a bunch of stuff here. Stop when we get done. Next, superconductors. So, Daniel asked about this last time. Superconductor is a material in which the resistivity is equal to 0.
Actually 0 or pretty close to 0?
So I'm not sure that it's, yeah, I'm going to go pretty close to 0. In theory, it's actually 0, but there are probably thermal effects that you really can't mitigate to 0. Okay, so there's 2 types. The first are low temperature superconductors. And by low temperature, we mean critical temperatures below 25 Kelvin. So if I'm plotting resistivity as a reminder from last time, as a function of temperature, it does something like this, and then boom, drops off. This is TC, the critical temperature below which it behaves as a superconductor. So, low temperature superconductors are primarily metals or alloys. These have a higher than average resistivity at room temperature. So they're not exceptionally good room temperature conductors. It is a reversible effect. That is, you heat it back up, the resistivity goes back up. The transition is 1 to 2 degrees wide. So it only happens over a very short temperature range, 1 to 2 degrees. Okay, so I've drawn it as essentially having a no width, but there's really a finite width, which it actually has. Okay. This is kind of one of the problems with the low temperature superconductors. The critical temperature goes down as current density. I don't know, what do you guys use for current density in E&M? Sigma, right?
Charge density.
That's charge density. What's current density? K?
Or J, actually, for
Are you doing volumetric or surface?
Volumetric.
J.
J. Okay. As J goes up. I'll just make sure I'm using the same symbols you guys use.
It's just amount of current.
In other words, the more current you pass through it, the lower you have, the colder you have to keep it in order to maintain superconducting properties. Or magnetic field. any kind of, whether it's charge density or magnetic field, either one, can drive the temperature down. The cause is synchronization. Synchronization of an electron pair vibration with lattice vibrations. So essentially what happens is you have an electron pair, called a Cooper pair, and they are resonating. They travel through the lattice, these two are sort of linked in resonance. And the lattice happens to resonate at the same frequency, so you basically can kind of imagine, it's not really a mechanical thing like this, you can imagine the lattice sort of opens just a gap at the same frequency that the pair wants to go through it. And so there's a synchronization between those two, allowing the pair to travel through without interaction from the lattice.
It's like you get all green lights on the main street.
It's like getting all green lights on the main street, yeah. So, but it's, that's why you have to be at very low temperatures, because at higher temperatures, you can't maintain those lattice vibrations. And can't maintain that synchronicity with the lattice vibrations. Because there's too much thermal excitation to get it going, to get the lattice behaving.
Why do Cooper pairs happen?
Why do they happen? It's been a long, I know this, but I don't remember. It's been a long time since I've talked about this stuff. I mean, like 25 years long. So I don't recall exactly what the foundations of it is. But nonetheless, that's the mechanism. Any other questions about the low temperature superconductors? Okay. Problem with low temperature superconductors is the low temperature, right? You got to use liquid helium typically to feed them. So I'm sure do we have an MRI? Does anybody have any idea whether the chemistry department has an MRI? An MR, actually, nuclear magnetic resonance instrument. You do? You do? So typically, a nuclear magnetic resonance coil is a superconductor, and it is cooled to liquid helium temperatures. They use low temperature superconductors in magnetic resonance imaging. And so so you constantly have to keep an NMR system or an MRI system fed with liquid helium in order to keep it cool. Yeah.
It doesn't actually use up liquid helium though, right? You just have to repressurize it.
No, you cannot insulate it well enough. So eventually heat makes it in and boils off the liquid helium.
But the liquid helium doesn't go anywhere, right? It still stays there. Because people talk about how we're running out of helium. And, right?
Yeah, well, yeah, because there's too much helium in the atmosphere.
But does the liquid helium actually go anywhere, or is it?
Yeah, it has to. It releases from the. So you have a closed system that has the liquid helium in it, but the heat from the environment comes in. You can't keep that perfectly insulated.
Right.
Right. There's still going to be heat leaking in and warming that liquid helium, which will drive the pressure up. Right. As it drives the pressure up, the helium burns off.
Does it go anywhere? Or does it stay?
I mean, even if it stays in the tank, I'm sure that there's probably
It's kind of recycling.
Yeah, I'm sure that, but I'm sure it boils out of the system. I mean, like you said, they try to recapture it, but it's still, you can't. It has to go somewhere.
Yeah, it's not 100%.
Right. So, and in fact, most of those NMR machines actually have a liquid helium core that is surrounded by a liquid nitrogen insulator. So they pour liquid nitrogen in it to keep as little heat as possible from getting into the liquid helium. Because liquid nitrogen is much easier to make and maintain, to buy than liquid helium. So they have the liquid helium core that you have to replace, where you have to replace the liquid helium, once a year or something. But then the liquid nitrogen surroundings have to be maintained on a more regular basis. So liquid helium within liquid nitrogen within an environment insulated within the room. all to keep it cold. Okay, anyway, in order to maintain superconductivity in these coils, so you can handle high current densities. Okay, that's one. What do you think the second type is? High temperature superconductors. Right, two.
Really low temperature superconductor.
No, it is not. High temperature superconductors. And by this we mean temperatures up to T sub C is greater than 25 Kelvin, but generally, most often, what we really care about is greater than 77 Kelvin. Why do we think greater than 77 Kelvin is a particularly important threshold? Anybody know?
That's the temperature of liquid nitrogen.
It is indeed. That is the temperature of liquid nitrogen. So if we can get them above 77, liquid nitrogen is something that we can actually manufacture and maintain fairly readily. Okay, so liquid nitrogen is not nearly as hard to get as liquid helium. All right, these are primarily ceramics rather than metals. Again, it's reversible. As they warm up, they lose their superconducting properties. The temperature width is a little bit wider now, 5 degrees C wide, so it's not quite as rapid a transition. It's even more sensitive to current densities or magnetic fields. And the cause is still being understood. So largely, there are in the first high temperature superconductor was YBCO, yttrium, boron, copper oxide. Is it boron or barium? Anyway, it's one of the other, YBCO. And it was, so it's a ceramic material, but there were planes of superconductivity in here. So there were certain atomic planes in the crystal structure that actually carried the superconducting properties. So the electrons were traveling along particular planes as opposed to just sort of randomly throughout the material, because again, they're ceramics. They don't have the Fermi sea of electrons, right, like the metals do. So it was very closely tied to the structure of the ceramic material.
So since,
You raised his hands.
do you know what the highest temperature superconductor is, or
I don't
I guess
know.
what is the highest temperature that you know of the first?
I don't know.
Yeah.
So, so how do you think, if they don't understand it, how do you think it is that they decided to use yttrium?
I honestly don't know where the foundation was. I mean, I'm guessing that they were making it for something else and saw it. You know, it's like Viagra. You know, seriously.
I know.
Viagra give you the giggles, yeah.
Well, I could say like Plato, right? Also developed for.
That's more video friendly.
Okay. So like Plato, they were investigating it for one purpose and found out, oh, look, it has these weird properties. I suspect that's how it happened. I don't know the sort of history of science kind of perspective. Although I wouldn't be surprised if Kyrus is back there looking it up even as we speak.
Which one, Plato or Viagra?
What are they trying to make when they stumbled upon Viagra?
High blood pressure, heart medicine. And still works. Actually, they use Viagra in children for that reason, for hypertension.
Come on.
Play-Doh, on the other hand, was developed as wallpaper based, to remove wallpapers. It was something that they tried to use. They developed
Play-Doh or silicone?
Play-Doh, not silicone.
Because it seems like Play-Doh.
No, Play-Doh was developed. They were trying to get wallpaper based off, and they were trying to make this thing that would adhere to wallpaper. That's what Play-Doh instead. Sticky notes also developed.
And erasers.
What's that?
And erasers.
Erasers.
I think I read that.
And there's also duct tape. There's duct tape, which does everything but the one thing it was actually designed to do, which is to like stop holes in like water ducts. And it's like the one thing it can't actually do.
Well, there you go.
It's barium.
Barium. Okay.
Why can't you hydrogen?
Liquid hydrogen is even more. It's an even colder system, and therefore even harder to maintain than helium.
accidental byproduct.
So it's so readily available that you can't maintain it, you can't get it.
No, it's a lot more energy involved in taking that. It's not so much, it's the energy of pumping something down to holding that cold temperature. It's easier to hold the cold temperature. Somebody, did you have a question, Cass?
I found this, well, Wikipedia, but it says that the highest temperature superconductor is 138 Kelvin, which is.
I was going with 120 would have been my guess, so 138 apparently. But the problem is they're made out of ceramics,
Yeah.
right? So they're more difficult to actually use as a, so typically what they'll do is they'll make take a ceramic powder and pack it inside of a silver tube and make a wire out of it, rather than actually having, you know, in order to make it. You gotta do what you gotta do.
Wouldn't it be like really hard to get it to those temperatures because like we had ceramics, you cool them, they just shatter?
That's, well, they would, not necessarily, right? The only time that they cool and shatter is if you have like a large piece and you cool the outside without being able to cool the inside, right? It's the thermal gradient that actually causes the stress. So if you have a small powder or a thin layer or something, you can cool it fairly uniformly and it's not a problem. Did you have something else over here?
I was, yeah, I could verify the temperature.
Okay. So I have 2 data points. And this one's not from Wikipedia, so you're. All right.
You know, smoking isn't the best thing for your health.
I'm trying to kick the habit, you know.
I know it's addicting.
All right.
And all of this is unfair.
Heroin is
I wonder sometimes if Dan's got like this whole, you know, list of comments that he's got saved up, that he's gonna just sort of when he gets back to.
I think he like. I think he gets.
That's very accurate, he will.
Yeah.
I think he like goes into your room, looks at your notes, and he's like, okay, I'm going to ask the question here, and talk about it then.
Other
day.
Other Dan.
He's Daniel.
Ah, I'm on DL.
What do we call him, Dan?
All right, let's go back. To
I'm calling you out, boy.
Okay. Remember what defines an insulator in terms of Fermi energy?
Wide gap.
Wide gap, exactly. Oh man.
Smoking, man.
Here's the max, we'll give you a
So we end up.
chocolate covered pill.
We just have a big gap for insulator. So that even at high temperatures, there's very few electrons excited into the conduction band. Actually, I guess I shouldn't fill this one, but nonetheless, you can get it. So there's very few electrons going to be excited from the valence band to the conduction band. So what happens then? Is that if I apply a field, a large electric field, applied electric field results in a charge buildup at the surface. Because there's no place for those charges to go because they can't get to the conduction band. And the density of those charges then related to the permittivity, the dielectric constant in the applied field.
Oh, that looks familiar.
So, man.
There's a water fountain out there.
Yeah, that's right. That's got to make it through another 13 minutes. It's not like I got a presentation to give her. So,
But you have a presentation you have to sit through.
yeah, well, I'm coughing now, it's okay. Anyway, so we got superconductors, we'll talk about semiconductors later. I'm gonna get to them, what day's today? Wednesday, Friday, we'll do semiconductors on Friday. Insulators, superconductors, radio conductors, I think we've covered most of those. The last thing I want to cover before we make sure we get to today, then last category of kind of electrical materials or electrical properties. Is a piezoelectric material. Piezoelectric materials. Everybody knows what a piezoelectric material is? You apply a force and it creates a voltage. Or you apply a voltage and it creates a stress. So piezoelectric tweeters, solid state, speakers, you apply the voltage and they move back and forth and you create a sound. But instead of having a diaphragm moving back and forth in a magnetic field, you've actually got the device itself moving back and forth. So the speakers in your, the little speaker in your used to be speakers back in your computer. Now everybody's got a multimedia computer, but back in the day, they would have little piezoelectric speakers in your computer just to make the bing sound. They weren't trying to make full multimedia kind of presentations.
In 1814.
That was unrelated.
Yeah, it was.
Okay, so here's what we get. Here's what happens. So I'm going to use barium titanate as an example. Barium titanate actually has a lot of cool uses, but I'll use it here for piezoelectric effects. So those are all the bariums. Let's go with the titanium is red, and that's in the body center. And then all the oxygens are blue, and they exist at the face centers. So, it's normally tetragonal, even though I've not necessarily drawn it here. So let's see.
What's the red?
What's that?
It's the 3 different.
Right. So what happens is the below 120 degrees C anyway is tetragonal. And the titanium is not exactly centered. The titanium atoms, this is a 4 plus, this is a 2 minus, and this is a 2 plus. So total barium titanate that. Okay. So normally the titanium ion is slightly displaced vertically, so that there's a dipole moment created in the cell. So, if I apply a field, I'll just do it in 2 dimensions. If I take my cell and apply an E field, like that, it tends to elongate the crystal because it pulls the titanium upward. You have a response, the dipole response to the applied field. Does that make sense? As positive charge goes up, negative charge goes down in response to the applied field. Similarly, if I apply the then opposing field, it squeezes it. So it's all built on the fact that there's this inherent dipole in the root structure of the crystal, and so it's a crystallographic feature. So if I have barium titanate powder, it's not going to exhibit this kind of behavior because the net effect is zero. Some of them are being pulled, some are being squeezed. So you have to have a single crystal in order to get this effect. Okay. The opposite then is also true. If I take this crystal and squeeze it, then I'm going to create an electric field or a voltage. So I can use it as a sensor. So if I have a piezoelectric material and I drop a ball on it, there will be a voltage spike when the ball hits it because it squeezed it and creates this potential. All right.
Is it linear with force? You apply a linear
No. I mean, you can approximate it as linear, but it's not. Even over small voltages, 10 volts or something, it won't be linear. So you'll have to do some kind of, at least a quadratic fit if you really wanted to get some kind of direct interpolation. In fact, nobody in here probably will. That's one of the labs that I do when I do a lab for optics, is I have a piezoelectric crystal, piezoelectric speaker, and mount a mirror to it and have students measure the displacement as a function of applied voltage. Because the displacement is typically microns on scale. So we build an interferometer, measure the displacement, and characterize that very curve that you're talking about. Characterize the relationship between applied voltage and physical displacement of the device. Yes?
So is the voltage when you press it, the voltage that actually pops up is it based off of the speed of travel of the crystal or the actual displacement?
It's based on the the actual displacement.
So it doesn't matter how fast you.
As long as it's truly insulated, then yes. As long as there's no opportunity for that charge to dissipate, for the voltage to dissipate, whatever, then yes. Any other questions? But displacement and load are directly correlated because it's an elastic material. Okay. So you still have it's modulus, so you can directly correlate the load to the displacement. But it's the physical displacement that changes the dipole moment that creates the voltage. Okay. All right, that's piezoelectric materials. Well, we got 4 minutes. We'll see how far I get. Next category, ferroelectric materials. So ferroelectric materials are polarized materials in which I can reverse the polarization.
Is that like electromagnetic?
No. It's a, well, like ferromagnetic materials. You familiar with, do you guys ever talk about ferromagnetic materials in UPhys?
It's not just regular magnets.
Well, most materials are ferromagnetic. Most of the magnets are ferromagnetic.
Isn't that where their bonds like aligned, align
Whether the magnetic fields are aligned.
their magnetic fields are aligned?
Right. So the point, it's kind of the same thing here, except instead of being magnetic field, the magnetic zones, we're talking about the dipole moments. So I can actually flip this. In reality, because the titanium is pushed up a little bit, the oxygens are pushed down a little bit. But I could flip it. If I could force the titanium down, I could get it to reverse its polarity. Right? So I have to kind of force the titanium through the oxygen atoms. You can imagine, if you use the solid sphere model, the oxygen atoms are kind of there. There's a space between them, but it's a space that's smaller than the titanium atom. But if I apply enough force, I could pop it through and then invert the polarization. That make sense? So what I might have a block of ferroelectric material. Get that even. Where these are all little arrows. Where there's a sort of a not random, but it's a variation in the orientation of the fields of these things. Did I do that one? No, I didn't. Okay. So this is sort of a microcosm of what's going on. So you have each of these unit cells in the barium titanate crystal, and these represent the orientation of the titanium. So the titanium here is offset to the left, here it's offset down to create the electric field. Does that make sense? Okay. But the average effect is 0. There's no, the net effect is that there's no electric field. But if I apply a field, let's say I apply this field, then I end up aligning all of the individual unit cells. You get the idea, I'm not going to draw all of them. I end up aligning all of them because the applied field then forces all the titanium to pop up in the same direction. And end up with a net upward polarization. So I can polarize a material that otherwise wasn't polarized by simply applying an electric field. And I end up inducing a dipole. So if I map the polarization as a function of the electric field, I start out with no polarization. It comes up and does something like this. And then as I reverse the polarization, it does this. And it does this. So in order, I polarize it. Then in order to unpolarize it, I've got to apply an opposite electric field. I've got to cancel out the field that's already in there. I have to force the titanium back. And in order to get to 0, I've got to go to an applied a negatively applied field. And if I keep going, then I flip all of them back, and there's net negative polarization. See what I'm saying? Kind of like once you deform something and you try to get it back, you can't get it back exactly right. So you bend it. Oh, now it's bent too far the other way. You bend, that kind of thing. Okay. And this is the saturation polarization, and this is the remnant polarization, P sub R. So the thing that's really useful about this, and this is where barium titanate's real, I mentioned it as a piezoelectric material, but this is actually its real utility, barium titanate. It makes it optically nonlinear. That is, light is an electric field. So as light interacts with the material, there's a P. It turns out the polarization is related to the. Here, I'll do it. Write it out. That's the polarization through nonlinear materials. Am I over time? I'll look at that one. I guess. Blake going to leave. Oh, okay. Anyway, the point is, the dielectric constant and polarization are related to each other. So that as I apply an electric field, I change the polarization, therefore I change the dielectric constant. So the light itself changes the dielectric constant of the material into which the light is propagated. So it makes it a nonlinear material. Did he leave his exam before he left?
Yes.
Anyway, it makes it really cool because you can do some really cool funky things with these crystals.
Are you gonna have a demonstration class?
I have no bearing name to give you a
Or a
demonstration.
YouTube video?
Yeah, actually, I could probably pull something up. If you remind me.
I really like your station.
It's not mine. That would be, Ellie's.
It's history, so.
It's a great color.
Yeah.
Presentation, guys.
Alright, I'm gonna select these. There's a what? We were talking about that earlier today.
Is that it?
I think it's just those four.
Four of us, unless it's Dan. Or Dan
No,
or
it's
you?
not coming back.
Oh, no.
I mean, next year.
Oh, okay.
Wow, it is hot. We haven't even started yet. Holy